In this video, I'm going to talk a bit about vectors. And as I said in a previous video, I don't want to spend a whole lot of time on this. So it's going to be, a very quick crash course on vectors. And I do have other videos in a linear algebra playlist where I go through some of the vector operations and things like that in a bit more detail and show sort of the geometric interpretation. But this is going to be a little bit more abstract than that. And so the first thing to talk about, so linear independence. So we want our basis vectors to be linearly independent, and we want them to span. And so linear independence is when we have our basis vectors times these components x here being equal to 0 only when all three of the components are 0. Because if that wasn't true, then we could express this one in terms of the other two, and therefore this one would not be independent. And so we need that to be linearly independent. We can't express one of our basis vectors in terms of the others. And so spanning is when any vector in our vector space V can be expressed in terms of the bases. And so spanning just means that there is no vector in our vector space that can't be expressed in terms of our bases. They span the entire vector space. And so if A1, A2, A3 are linearly independent and span the vector space, then they can be used as basis vectors. And obviously, it's always nice if we can have orthonormal basis vectors, but that is not a necessity for basis vectors. And when you get into like space groups and stuff like that, you often find that it's not that good to have orthonormal basis vectors, that you want basis vectors that fit your sort of lattice more usefully. And so more generally, a linear vector space in which it is impossible to find more than n vectors with the property of linear independence is a space of n dimensions. And so once you get to the point where you have basis vectors which can't be expressed in terms of any of the other basis vectors, then however many basis vectors you have is the dimensionality of your space. So vectors are expressed as a linear combination of the basis vectors, each multiplied by a component. And so we can take the row vector of our bases and then this column vector of our components, and we can just do a dot product or scalar product of them, and so we end up with this. So there's the summation here. We can have the implied summation. Then a transformation gives a new set of basis vectors in terms of the old set of basis vectors. And so we have our E tilde here, so that's the new basis vector. And so for each I, we go through the R1, then it has an I because that's the one we want to use for it, and multiply it by each of these basis vectors, because that will give us the new basis vector in terms of all the old basis vectors. So we can collect each of these numbers here into a matrix, of sort of arbitrary size here. Well, it's arbitrary, but it depends on the dimensionality of your vector space, which could be any n-dimensional space. So we could write it more simply like this. So this is with the Einstein summation convention, which these repeated indices here, the I and that I there, it's implied that those are summed over. And conversely, we can express the old basis vectors in terms of the new ones, and so this is the inverse of that, where we are expressing the old ones in terms of the new ones with the Einstein summation convention here. And so we can take two of our matrices here, Well, we take 1 and then its inverse, and that gives us the identity element, which is this I sub n, with the n being the dimensionality of the space. And so to do a mapping, we need the components of the new vector, so this v prime, to be the same in the new basis. So we need the components to be the same in the new basis as the components were for the old vector in the old basis. And so that's essentially saying that if we have, our basis that looks like this, and we have some vector there, once we sort of rotate these basis vectors, the vector will still have the same components in the basis vectors. So I guess we could even do a scaling on this, and then this would have to be scaled the same amount. And so, the bases here are, or the components rather, are going to be the same in both of these. And so sort of the basis and the vector are being rotated and scaled the same amount at the same time. We therefore have a mapping, which is this phi, which goes from the unprimed to the prime. And so we can think about it in terms of this operator here, which could be like our symmetry operation on the components and the bases here, and that gives us the new bases and components at the same time here. And in fact, yeah, so never mind. I thought I needed to flip some indices, but I shouldn't have to, because we are not going into the dual space here. But anyway, our R is therefore an operation such that our primed vector here is equal to the operation on the unprimed, and this should be a vector right there. And then that's equal to this M here, which is a matrix, such that our operation, our symmetry operation, whatever operation you want to call it, on the vector is equal to the matrix being operated on the vector there. So if we look at our C3V group, we can express it in these two different bases here. So we could have this basis here, or we can have this basis here, where this one is the orthonormal right here. So then a 120-degree counterclockwise rotation in the one on the left will give us the new bases that look like this. So this is the new basis in terms of the old. This is the new basis in terms of the old. So what we see, so we're rotating at 120 degrees. So this E2 is now going to be down here. It's going to be essentially like that. And the E1 is essentially becoming the E2, and that's why E1 is 0 times E1, and then E2, so it's essentially just E1 equals E2 now, where this is negative because we're essentially, in the old basis, we're saying that we go sort of negative that way, then the negative of that one, which brings us down to there. And so that gives us a matrix that looks like this, where we see on the left side we have the components we had here, and on the right side we have the components we had over here. And so this operation here, the C3, the 120-degree rotation acting on our basis vectors here, gives us this matrix acting on the basis vectors. And so that is in that form that I had above, where I had the R acting on our vector equal to our matrix acting on our vector. And so if we do it in the other basis, and so that's this orthonormal basis, we have these right here as well. These are the new bases here in terms of the old bases. And in fact, I should probably put like a prime next to these these right here to show that these are the new bases here. And so this gives us this matrix, and so that is just one of the matrices that we saw in an earlier video. So this is just one of those matrices that that we mapped our C3 symmetry operation onto in a previous video when I showed that set of matrices that were representations of our C3V symmetry group. And so those were isomorphic. These matrices are isomorphic to the C3V symmetry group. All right, so we have this mapping, so phi, where we're mapping our symmetry operations, our group elements onto these matrices here. We can show that these matrices are a group because they're closed under matrix multiplication, they're associative, they have an identity element, and they can have an inverse. So in general, giving a vector space V sub I a mapping phi from our symmetry group, G here, into matrices is given by this, where the subscript I in our mapping here denotes that this is for a particular vector space VI. And so that's kind of what we were showing up here is depending on the basis, you're going to map into a different group of matrices. And so this one gave us matrices that would be more of a form like this, where the basis on the right here gave us one that would look more like this. And so it depends on your vector space what matrices you actually map onto. And so when we do this mapping here from our group elements to, remember this D is that that sort of function that brings us from group elements to matrices. So like I said, the I is to tell us that we're in that vector space. So for example, if we're in the vector space V sub 1, which is a 1D vector space, and in fact it's a 1D vector space that's only positive, and so we start at 0 as our origin, and we just have the sort of positive number line here, then our C3V can all map onto the number 1. And because 1 times 1 is just going to always be equal to 1, and so you take any element of the group and act it on another element of the group, and you'll get another element of the group because everything in the group is just 1. Or we can have this V2, which is a 1D vector space, but now we are adding in the negative numbers. So we have 0 here, we have -1 and +1 there. And so we can map our C3V elements onto either 1 or -1. So I showed that in an earlier video. And so that gives us a group with just elements 1 and -1, but then we can take our V sub 3 to be a 2D vector space with orthonormal bases and map our C3V onto it, and that gives us the matrices that we saw in an earlier video. And so this table, we can see we have our group elements there, and these are the things we map it onto when I equals 1. These are when it's I equals 2, and this is when I equals 3. And of course, you could have D4 where you have a different set of bases, or D5, which is yet another set of bases. And so there are a ton of representations, of matrix representations you could map our C3V onto. And so it's always just kind of which one is the most useful, and as we'll talk about later, we want to get to kind of the irreducible representations, but I won't go into that right now. And so the matrices, which is this D3 of R here, so this function of our symmetry operations, are dependent on the vector space being this, because if we changed bases, then we would have different group of matrix representations. So when we perform our symmetry operation R on the basis vectors, we get this. And so this is just showing that in one basis, we are doing this symmetry operation, and it gives us this matrix. In a different basis, it gives us this other matrix. And so we can show that when we do our symmetry operation on this tilde basis here, that is equal to our symmetry operation on the untilted basis here, but we have this t sub ji here, which is a matrix that is actually changing the basis. So this is a basis change matrix. And so because this R is, acting on the basis is just equal to the matrix acting on the basis, we can just change it into this matrix here. Then we can multiply through by the inverse of t, and we end up with this. And so it gives us the relationship between the m tilde and this m as being this here, which is just the similarity transformation, and they are described as equivalent. So this tilde matrix here and this untilted matrix here are described as equivalent, and they are equivalent through this similarity transformation. And since a transformation in the first is this ms equals p, then m tilde s tilde equals p tilde, such that we are just using this t inverse and t here, and then we sort of replace this p with the ms here, and so we end up getting this. And so this, what does this similarity transformation mean? So we got this similarity transformation here. What is sort of the intuition behind it? And so if we have two vectors related to each other by some matrix S, but in a new basis they are related to each other by a matrix T. So these primed the primed W and the primed V here are related by T, where the unprimed are related by S. Then we have the basis transformation for each with this matrix P, so that this P acting on V gives us V prime, this P acting on W gives us W prime. And so we know that we have this W prime equals T V prime, and then we can just use the P on our W, because that is the same as the W prime over here. And then we have the P V here, because that is the same as the V prime there. We multiply through by the inverse of P. On this side, the inverse acting on the P there will give us the identity matrix. It gives us this on this side, which we can kind of put in parentheses here. So W equals this thing in parentheses here acting on V, and so we know that W equals S acting on V, and so we have S equals this. And essentially what it's doing is, because you start from right to left with matrices, so when we have our P minus 1 SP acting on our V here, we first do P, which gives us P minus 1 S V prime. Then we do this S on here, which gives us P minus 1 W prime, and then we act the P inverse on there, which brings us back to W, to the W there. And so you're essentially, you change the basis P, then you perform your simpler transformation, which is kind of the reason you would even want to do this, is because we are doing a simpler transformation. I think I put S in here. This should be T here, so we're using our T there. So the simple transformation T, then we change back to the old basis, and so you transform to the easy basis, do the easier transformation, then transform back to the old basis, and that's sort of the reason you would even want to do this. But what we were showing up here is just that this similarity transformation is just telling us how we can go essentially from one matrix representation of our group to a different matrix representation of our group. But anyway, well, yeah, I hope you found this video helpful. Probably the next couple videos will still be on vectors before we get, really into like point groups and things like that, which is kind of the main impetus behind even making this playlist, which is why I'm kind of hurrying through the vector stuff a little bit. But anyway, I hope this made sense to you. Maybe if you already know a little bit about vectors, then maybe this made some sense to you and helped clear some things up. But anyway, I will see you in the next video.